the meaning of structural dynamics and how to derive equational motions for a given dynamic system. We have several ways, and you have a homework to practice how can we use these principles to derive equational motion for a system. And I just checked, and I found that about 1/3 of the students, they didn't submit your homework. I don't know why, but if you are not, you don't have the textbook or other reasons, I think you can submit your homework together with the second one, okay, which is today's homework. You can submit your first homework together with the second one. And I will check your homework, and if any common problems there, I will organize a special, maybe special time, then we can discuss about all these problems or difficulties you may have in your homework. So last week we have one small topic we didn't discuss, which is shown here on the screen, effect of gravity or static force. So when we derive equational motions, do we need to consider about the gravity force or static force? We will discuss this. So let's see this system, this single degree of freedom system shown on the screen. And you can see on the very left, finger A, the system is on its very original position. By the very original, I mean that the stiffness, the K here, they have no force there. It's undeformed state, which means there's a zero deformation of the springs. And if we very slowly release this system, very, very slowly, and allow this system to be statically equilibrium position, which is the second finger B, you can see on the screen, which is a static equilibrium state. And here, the spring has elongation, or it has deformation. And because this is a static problem, or this is the static state, so this deformation, delta st shown here, should be equal to what? Anyone?
mg over k.
Yes, it should be W divided by K. So it should be W over K, because it's a static one, like F goes to X, so it should be W divided by K. So remember this, okay? Then at this position, which is a static equilibrium position, we apply a dynamic load to the system, which is PT, shown on finger C. You can see here, finger C, we have a dynamic load applied to this system, and which is PT here. And we take this position. Sorry, I need actually to get my mouse back. I don't have a mouse there. Let me close this first. Oh, here. So you can see if we use this position, which is the static equilibrium position, as the origin for the dynamic vibration, which means this is the reference position for the dynamic displacement or deformation here. So we apply a dynamic load here, and then as this case, at this station, we can derive the equational motion for this system. And then we cut free of this system here. Then we draw all these forces applied to this system. You can see we have external force, which is PT, and you have gravity force, which is W, and you have restoring force, which is back to the original position. So the direction should be this way. So it should be this way. So this is a dynamic restoring force here. And this is damping force. So damping force is also push the structure back to this original position. So it should be this direction, okay, this direction. And if we use the D'Alembert principle, we can introduce the initial force here, the initial force. So the initial force should be opposite to the movement direction. So it should be this way, because this is positive. This is a positive direction. You can see here, this is positive direction. So the external force, the internal force should be this way, right? This way here. So this is all the force applied to the structures, to the system. Then we can use the balance of all this force. I'll try again to write it here. So you can see we have Fi, which is initial force, and plus the damping force, which is St here, and then plus the restoring force, which is Fs, and it should equals to the force in this direction, right? So we should be Pt. I just use P here to make it simple for me. Write it. So we have this balance, the balance of all the forces, and we can introduce all these things into this equation for the initial force. For the initial force, it should be m times the acceleration, which is ut here, right? Ut, this one, ut plus delta st. Then, or you can just use the I just use delta st here. Then you have two dots, right? Two dots here. And the damping force is only related to the relative displacement, relative velocity. So you should start here. So it should be c, then u dot, because it's only respond to the relative velocity. So its reference position is here. And the restoring force should be k. And you have static one, I just use delta here, and also dynamic one, with dynamic one here, ut. I just cancel the t. So you should t plus delta, plus w, plus w. And because this is constant, so this is canceled due to the differential operation. So finally we got mu2 here, mu two dots, plus c dot, cu dot, right, cu dot. Then if you use this is k delta. K delta, remember this is w, right? As I just mentioned, this k delta equals to w. And then it should be ku and qu. And because we have a w here on both sides of the equation, so we can cancel this. So we cancel this, and cancel this, so it equals to p. So it equals to p. Which means if you use the static equilibrium position as a reference position for deriving the equation of motions, you can cancel the gravity force, or you can cancel the static force. Let's say you can cancel the static force. This is a very, very useful idea or principle. So you need use the static equilibrium position. So at all the homework we may have later, or the quiz or the final examination, if we have one, if I mention that, please derive the equation of motion for the system from the static equilibrium position, which means you don't need to consider about the gravity force. Unless I said you must consider the gravity force, So why I said this is a very useful principle idea, because at other situation, here is a very theoretical example. At other situation, we can use this idea to simplify this a problem. Let's see if we have high-rise building subjected to wind load, wind load. And the wind load, normally we can decompose the wind load to two components. One component we see it is mean wind speed. If you're familiar with, I guess you know this. And the other component, the second component we call it turbulence component. So this is a constant, which is mean wind speed, and this is dynamic, is turbulence wind component. And due to this one, which is a constant one, right? This is a constant force. It's like the gravity force. So they push the structure away. That's very simple. I just sorry, this is not a good position. It should be start from here. Anyway, I think you will understand what I'm trying to describe. Not this one. I did not this one. I can't cancel this. I think I have Robert. Oh no. Cancel service. I repeat this. The first component is the mean wind speed. Mean wind speed. Mean, M-E-A-N, mean wind speed. Okay, mean wind speed. That's simple. This is a high-rise building. Let's use this simple. And you have wind, which is mean wind speed, push the structure away from its position, original position. So this position is like here, which is the static equilibrium position, because you have mean wind speed, which is a constant embedded. You can, if you can see the screen, see my gesture, you can see this is a tall building. You have wind speed, which is mean wind speed, which push this structure away. So from its original position. Then at this position, if we consider about the dynamic one, which is a turbulence component, then the structure starts to vibrate. Okay, like this, it vibrates. So it starts to vibrate. So it's quite like here. If we apply this PT is like turbulence wind, then the structure vibrates against this position, okay, against this so-called static equilibrium position. So by this way, we can, you can simplify this analysis by two. One is a static one is a dynamic one, okay? So this is a static one. First, you can calculate the static position here. Then you can calculate the dynamic one. So dynamic one. So if you also understand here, this usually as a design, for the design purpose, we worry about maximum displacement or maximum deformation. Okay, so this one is a static one. Okay, this one is a static one. And this one is a total one, which is the static one plus the dynamic one. Okay, so if we'll first calculate this. So this is easy because this is a static problem. Okay, static problem. And the final one, you can plus a coefficient here, which is like here. We can use this idea, and this coefficient we can calculate actually here. Okay, actually this part. Okay, this part is we can by many calculation we can describe this part as mu delta. This mu is a coefficient. So the final deformation of this high-rise building due to wind, you can express it like this one. So which means if you calculate the static one, and then you calculate the dynamic coefficient, then you can easily use this equation to estimate the maximum deformation of the structure due to a wind, due to a strong wind. So this is very common. This is very common. And actually, we use this idea, at least in China, we use this idea to calculate the response of high-rise building due to wind. We give you this coefficient. After many calculations beforehand, then we can give you this. So you can just calculate this one for a given structure. Then you can use this idea to calculate the maximum deformation. So this is very useful idea. Another example I can show you is like if you have a bridge or beam, you have a train which is running across this bridge. Okay, the dynamic loads applied to this due to this the train or vehicle. Again, it's two parts. One part is a static one, and the other part is like a dynamic one, due to the roughness of the surface or the vibration of the structure. So again, you have two parts. One part is like static problem. The other is the dynamic one. So again, you can decompose this. Decompose this. You can two position or two parts. You can separate them. And we do use this idea for like running train, a vehicle across the bridge. What is the maximum deformation of the bridge due to this running train or running vehicle? So this is a very simple, you see, but it's a very useful idea. Very, very useful idea. So for this reason, we usually formulate a dynamic analysis problem from a linear system with its static equilibrium position as a reference position. So the total displacement force obtained by adding the static one together with the dynamic response. Okay, the dynamic response. The total response is obtained by the so-called superposition principle. So superposition principle. So we can use this idea to solve like static analysis due to dead load and live load. Live load, also we mean dynamic load. So you can solve two kind of problems, then add them together. So there are limitations for this part, because as you can see, that the static force will disappear from the equation of motion if the system is a linear one. Okay, if it is a linear one, because you use the superposition principle. Okay, the superposition let me go back here. The superposition principle applies only for linear system. So you can use this only for linear system. If it's a nonlinear one, it's a nonlinear case, you must derive the equation of motion from the very beginning. Let me go back. So if this K is it's not a linear one, we use linear stiffness just now. If this is a nonlinear one, you cannot derive the equation from this position. Okay, because a nonlinear case, the force depends on its history. So how it's vary from here to here. So you must derive the equation from this position. You cannot use this one, because this is only applicable to linear system. The linear system. So this is one thing. The other thing is the movement of the base movement under situation. So when you derive the equation of motion, sometimes you will deal with a case like this. There's no external force. Okay, there's no external force. There's the movements of the basement, like earthquakes. If there's earthquakes, so at the foundation of the structure. So if you have earthquakes applied here, the basement is moving, and because this is an elastic structure, so it starts to vibrate. Okay, due to the initial force, it starts to vibrate. So it seems there's no external force, right? There's no external force like applied here. No, it's just the movement of the basement. So this is a special case we call base movements, or sometimes like we draw it like this. So this is a base, and this is 1K, and this is a C, and this is the mass. And normally we have force applied here, but this time no. This movements of this basement. Okay, the support is movement. The support is movement. There is no external force like this. So for this case, how we derive the equation of motion? Let's see here. So this is original position. Okay, this is original position of the structure of the system, and it start to move due to the base movement. And this is its position at time instant t. Okay, time instant t. So at this position, we know the force applied to the structure includes three. So one is the initial force due to the acceleration. So if you use this, you see this is a relative displacement. Okay, relative displacement of the structure. Not actually, it should be like this. It's be easy for you to maybe understand. So this is original position, and it moves here, and moves here, and it had vibration here. So we need to cancel this. And this is the U here, which is a relative displacement due to against the position. So this is due to the movement of the base. So this part is due to the movement of the base. Okay, movement of the base. So this is movement of the base, and this is vibration. You can think like this is move here, and of course, the procedure starts to vibrate, but you can separate this. You can separate this. Please move, then vibrate, then move, vibrate. So from here, we can know the equation of motions. The initial force is two parts. It depends on all the acceleration. So one acceleration here, so one acceleration here. So it's add them together. We got this. This is the total initial force. And again, the restoring the damping force. The damping force is depends on the relative velocity, which means that it should be against here. It's be against here. You see, if there's no relative velocity, it's a rigid body. It's a rigid body moves here. There's no damping force because there's no relative velocity. So no relative velocity. So it should be this part, U dot, just against this one, U dot, U dot. Similarly, the K is KU, which is a relative displacement. Like the K is easy to explain. If you move here, just here is a rigid one, okay, rigid one. It moves here, and there's no restoring force because there's no deformation. Okay, no deformation. Only you have this deformation. They have the restoring force, pushing the structure back to this position. So the K also relative to the restoring force only depends on the relative deformation, relative displacement here. So it's U, this one. And this is the equation of motions. And if we push, we rearrange this equation. We'll put this UG thing to the right side of the equation here, which is minus MUG two dots. So this is the final equation for the base moment, Here's one thing I need to remember you. This value or this variable is relative displacement. Okay, it's relative displacement. If you like to know the absolute displacement of the structure due to the earthquake, you should add this one with this one. Okay, similar like we just discussed about the static force. This first static, then the dynamic. This is, you see, this is very clear. The actual deformation of this one, it should be this part plus this part. So plus this. This is just a relative displacement, not the absolute displacement. So this is one form. Okay, this is one form. If you are using a different form, sometimes you may see this equation of motion from a different, in a different form. It's like this is in relative displacement or relative variable. Sometimes you can use it in absolute variables. Use the UT here. So this, in this case, the first thing will become UT two dots, right? Because this measure from here. So this is the total acceleration. And the C, the damping force, because the damping force depends on the relative displacement. So it should be, if you use UT, it should be U dot T minus u dot. Okay, minus u dot. Similarly for the k, for the restoring force, it should be k because it depends on the relative displacement here. Sorry, ug. Here it should be ug. Sorry, ug here. And this one is a u t minus ug, which is movement of the ground or the base, and equals to 0. Okay, equals to 0. And you can move this c times this part, k times this part to the right side of the equation. And the right side of the equation it will become like c u g dot plus put plus k u g. But at the left side of this equation will become here like ut and ut, and this part will become this one. So two form. Okay, let me summarize this. Two form. One form is like in relative displacement shown here without this red part, and the other is you can express the system in absolute variable or absolute displacement, which will be this part. Okay, this part, and the right side will be this one. This one. So there's a difference between these two expressions. You need to understand what value you get from the equation of motion. Is a relative one or an absolute one? Relative displacement or absolute displacement. Okay, this is the first part, how to derive the equation of motion. Any questions?
Yeah, I have a question.
Please.
I have a question actually about the spring and mass system. What if the spring is deforming? Like for example, if the spring is connected to a rod and maybe like or a bar, and the bar is also having like a deformation, vertical deformation with the spring, can we still use the static equilibrium state?
Can you repeat your question slowly?
Okay, I mean, if for example the spring is connected to a bar, maybe like a horizontal bar, and the bar
The spring is connected to a what?
Maybe like a rod or a bar.
A bar?
Maybe let's say a beam. Okay, we can say like maybe a horizontal beam, and the beam is having maybe a vertical displacement and the spring also. Can we still use the static equilibrium state? If the
Can you draw something and show me? I can understand your question. You mean a spring connected to something? Then can we still use like one?
I have one displacement. Yeah.
But I cannot. What's the meaning? This still connect.
Yeah. For example, we have like let's say the spring is having like deformation, like vertical deformation, and we also have another, let's say a beam, and the beam also is having displacement. So the beam and maybe the spring are also moving, like both of them are having displacement. Can we still use this the static equilibrium state to define this vibration?
You mean like this? You have beam here. You have spring here.
And
you have a K here. You have a beam here. Right? It's like this. Of course, you still can use this. This as long as it's a linear one. This one is simple. You can. This is actually like here. I think similar to your homework. If you have one homework, you have one spring here, which represents this beam, and another spring here, which is represents this one. So that the two springs are connected in serial. So if we set this one is K1, okay, this one is K2. Like it's similar. If you simple this example is like this. So this is a two springs in serial. You can use the equivalent stiffness for this one, and because this is a beam, it should be, if I remember correctly, it should be 48
Yes, yes, yes.
divided by EIL power of 3, something like that. So you should have an equivalent K for these two springs in serial, which is K equals K1 times K2 divided by K1 plus K2. Is that your question?
Yeah, so I mean like we can just combine, like we can combine the displacement of like two of them, then extract from the static equilibrium state, right? It's possible. Okay.
Yes, of course. If you are meaning this problem, of course you can separate these two.
Okay.
So which by my understanding, the dynamic one is calculated by these two. The static one is due to they have a gravity force applied to this this beam. Okay, this beam. Then you have a static deformation due to this gravity.
Okay,
Then you can
and
apply these two together.
okay, and my second question is, can you give like one example of nonlinear system, because I'm not very familiar with nonlinear
No,
system.
I will not give you here because it's too personal and we are not. Later, I think maybe another time I can explain this. If we have a background here, I can explain this to you. Okay.
Thank
So
you.
for example, actually it's like this. If you have a spring, normally we have the restoring force like Kx, right? So squared, nonlinear. Okay, that's nonlinear. Or you have let's say you have a K which times like this one, not linear one. It's a nonlinear spring. So in that case, you need to start from here. Okay.
Thank you very much.
So which means this is linear and this is nonlinear. Okay, this is nonlinear. Nonlinear means that the force and the deformation or the displacement, they are not linearly connected. Okay. So I think if you have anything related to this, if your homework, I will check your homework first. I see someone send me a message. He maybe didn't understand about the assignments. I think like assignment like this is it's not from structural dynamics. It's from structural analysis. You have two springs connected together. So how we derive the equivalent stiffness? This is not my teaching topic. Okay, this should be related to some previous course like structural mechanics. Okay, structural analysis. I don't know exact name in your university. So if you don't know how to calculate the two springs, the equivalent stiffness of these two springs, I suggest you to refer to your previous textbook. Okay, because this is from last chapter lecture, we still have new one to start today. I will.
Professor, can I ask a question?
Sure. Please.
I have a question related to this 38 number slide. How can we?
This one here.
Yes, sir. Yes, sir.
Okay.
And I have.
Please.
And I have confusion, and I want to see if how can we represent this P effective T equal to minus mu double dot G in this figure. How can we represent this force?
How to what? How to get this one P equivalent force?
Yeah, yes, sir. P effective T equals to minus mu double dot G.
How we get this?
No, sir. How can we show in the figure?
Oh, it's like this. We'll not use this again in this finger. If you have this equivalent force, which is let me roll this again. It's too difficult for the online to roll something. It's is finally like this. You have the force applied here, which is P effective, which means we change this base moment case into a normal case, like you have M here, you have K, you have C. Just now you have the movement of the basement here, right? The movement of basement. And if we can change or use this equivalent force, which is like we apply this equivalent force to this mass, and then we can calculate the response of this mass due to this equivalent force. You can get U, which is this U, okay, this U, which means the relative displacement. So you don't need to show in the effect force here.
The P effective
Is this your
must
question?
be left. The P effective must be in left direction, sir, Professor.
What?
In
Again?
that STOF, the P effective you have written in STOF system, that must be pointed in left direction.
I'm sorry, I didn't hear you clearly. Can you repeat your question?
Okay, you have drawn the STOF system, and the P
STOF
effective,
system, yes.
the P effective is in right direction.
You can
from
have a
this-
minus there. It doesn't, because this is a positive one. When you calculate this, you have a minus here, so it doesn't, because I show this direction, because this is the right direction, the positive direction. So I use this PF here, but you have minus. When you calculate, you have a minus. So, and in fact, this minus doesn't matters. It doesn't matter because this is earthquake is force and back. So and we usually consider about the maximum U. It doesn't concern about the directions, which right or left. So this minus it doesn't means very. And doesn't very important. Doesn't mean very important.
Shall I ask one question more?
Please make it short.
Oh, okay, sir. You have written mu double dot t plus c u dot t minus uz, and I think that u
Displacement or initial velocity to the system. So initial velocity or initial displacement or initial velocity at the time instant zero. So at the time instant zero. So this is all the conditions we have for this problem. So this is equation of motion. This is initial conditions, and then we need to calculate responses of this one. This is U. We need to know what is U due to this U0 or U0 dot. U0 dot. This actually a differential equation. Okay, this is a second order non-homogeneous linear differential equation of the second order. If you need the complete term for this equation, so we need to know how to solve this. So let me review this. This should be knowledge from the advanced mathematics. We have this course in Tongji. I think you may have the same, maybe different title. So advanced mathematics. So from that course, you know the solution theory for non-homogeneous linear differential equation of the second order showing like this. You have two parts, right? You have two parts. One is this part, one is this part. Okay, time is up for the first lecture. Let's have a break. It's a long one. So we start our lecture at 10 o'clock, Beijing time, okay? So any questions you can ask me.
Respected teacher, would you like to share these slides?
Sure, I already upload the first slide, I think, to the Canvas system. After each lecture, I will upload my lecture.
Previous slides are not present on canvas.
I see. I already uploaded. Let me check.
Yeah, it was there, sir.
I have it on canvas. It's okay. It's okay.
Yes, there is the files in Canvas.
Yeah, it's not in the assignment in the files folder. It's there's a folder titled file, file or files. You can find the PPT the lecture there.
Okay, thank you, sir. Thank you.
Excuse me, Professor.
Mm-hmm.
Sir, I have a request and a suggestion, if you don't mind.
Please.
Sir, we have almost 25-minute long break, so I was thinking like we can take a break for 5 minutes, and then we can start our class, and we can at the end we can finish our class 20 minutes earlier. So because we are still in the long break, sitting in front of screen, so I think it's a good idea to start the class after 5 minute short break, if you don't mind.
Okay, I know because this is the university's requirements. This is a cost, and we have the schedule here. I need apply this for the changing. Maybe next week we can change this.
Okay,
We
sir.
can
Thank
short
you
the
so
long
much.
break, but this week I cannot do this because if I like I start earlier, then close the lecture earlier, I may have trouble.
Okay, sir. Okay, sir.
They,
Thank you
they
so
call
much.
this teaching accident.
Okay, sir. Thank you,
I
Professor.
will apply. I know. I also like to change this. We have maybe 10 minutes break between each lecture, so we can start earlier. We can close earlier. We can stop earlier. But because
Yes.
now I need to follow the schedule. Okay, I'm sorry for that.
Okay, sir. It's okay, sir. Thank you so much.
Hmm. Maybe next week we can change. I need to apply first. When I get permission, I can change this.
No problem, sir.
Okay. Okay, enjoy a break. Vision of the second order here. So we need to review the solution theory for this problem. Showing here that the solution of this equation can be expressed in two parts. One part we call complementary solution, which is the solution when this equation is a homogeneous one, which means ft equals to 0. This becomes 0. And this is also we call transient vibration or eigenvibration problem. And the second part is a particular solution, which is depends on the external force or the equation, the form of this part ft due to the ft. This is also called steady state vibration or stationary vibration. So in today's lecture, we only consider about this part. Okay. In chapter 3, we will start to consider about the particular solution due to external force. So now it's a 0 here. So it's for the complementary solution part. And to solve this problem, which is mx2 dots plus k equals to 0, right? Plus 0 without c. There are basically two ways. If you see the textbook, one is by Professor Chopra, one is by Professor Clark. They have two ways to solve this problem. The first way is very simple. The first way is so-called by the observation, which means like here. I'm not sure if we can have this video work. We can observe if you have a FTF system, you have a structure, you push it away from its original position, introduce initial displacement, like you have a mass here, you pull this structure away from its original position, then suddenly release. Okay, someone please turn off your microphone. Then if you observe this, you will find this vibrate like this, which is a harmonic one. It's a cosine function. You can use a cosine function or sine function to describe its movement due to the initial conditions. So this is from the observation, which means for this for this equational motion, for this undamped SDF system, from the observation, we know that the general solution to this free vibration system will have this form. Will have this form, which can be expressed as A1 times cosine omega t plus B2 sine omega t. So sine omega t. So there are two unknown coefficients. So A1, A2. We need to determine this using the initial condition. So to do that, before that we know because we need initial velocity, so we have initial velocity here. We have a expression for velocity here, and we have the expression for the acceleration here. So acceleration here. So to determine these two unknown coefficients, A1, A2, we can introduce the initial conditions. So if you introduce the initial condition with the time equals to 0, right? The initial displacement, so t equals to 0. So this part became 0 because you have t equals to 0. Oh, sorry, I started the recording. Okay. So if you have t equals to 0 here, so this part became 0, and this became 1. Okay, this became 1, and this is u0, right? u0. So a1 equals to u0, right? a1 equals to u0. And you have the initial displacement. So this time 0, so it became u dot 0. And again, this part became 0, right? This part, because this is time 0, and this part becomes 1. And so the A2 equals to u0 dot divided by omega. So divided by omega. So by these two initial conditions, you can have the answers for the two unknown coefficients. So which means if you introduce initial conditions, you can have the two unknowns. So this is the final solution for the free vibration of an undamped SDF system. So this is this is the final solution for this case. I'm afraid you have to remember this equation. Okay, you need to remember, or you need to know how we get the solution. Like I just show you how we get this. We know the expression of the final solution, which is A1 times cosine omega t plus A2 times sine omega t. But this is from the observation, it's a harmonic. And then introduce the initial conditions, you can determine these two coefficients, which is u0 and u0 dot over divided by omega, so divided by omega. So this describes the free vibration of a SDF system due to initial conditions. So this is a very important equation here. And you may have different form for this equation. So this is one form or one general form you can see in many textbooks like here. And or you can use these expressions for the free vibration of SDF system without anything. So it's A cosine omega t minus beta. So minus beta. So what is A? The amplitude, right? The vibration amplitude. So if you use trigonometric rules, you can, because A should be this squared and this part squared, and then square root. So it should be this part. Okay, this part. And if you express this thing, use the trigonometric equations, you can have cosine omega t times cosine beta, right? Cosine beta. Then minus, two minus, then sine omega t, then sine omega t times sine beta. Try my best. Then you have A out, you have A here, which it expresses using the trigonometric method. And then you see this is sine, this is cosine, so they divided this two, which is this part, because this is this one, and divided by this one. So you have, this is should be tangent, right? Tangent beta. The tangent beta is this one divided by this one, and this one is this part. And cosine beta is this part, u0, without this 2 here. Then it should be u0 divided by omega, then u0, then arctangent. This is beta. So this is, so how you determine beta? You determine beta here. And also you can see some other textbook. It's like 0 cosine omega t plus theta. Here's minus. You can use plus. So if you have the plus, it should be a minus here, the minus here. So if you have like the rho is the same because this is amplitude, and the theta, well, you have a minus here. So sometimes you need be very careful because different books they usually use different expressions. So there's no error. It's not wrong. So if you plus or minus, they're not wrong. They just different expressions. And even in some textbook, we can see it should be a sine omega t minus or plus beta. So you can also see these expressions. So if sine is two, well, upside, so upside down. This one up and this one down, because this part became sine, this part became cosine. And again, you need now pay attention to the expressions you are using. So they may have different form and different ways to calculate the beta. We call this later we'll know this is very important, the beta. We call phase delay or phase angle. So this is one way. One way we get this solution for free vibration of an undamped SDF system. And in the textbook by Professor Chopra, Professor Kraft, he used a different way. So I think I need to explain this to you, otherwise you may get lost by reading his textbook. So Professor Chopra, Professor Kraft gave this way. So from the mathematical theory, we know that the solution to this equation, this is a differential equation, linear homogeneous second order differential equations. And the solution should like this, okay, it should like this. So UT, A, E, S, T, S, T. The A here is the amplitude, and the S is unknown coefficient, so unknown coefficient. So then we can get we bring this into this equation, okay, bring this into this equation. We will have the so-called characteristic equations, because you bring A, E, S, T here, so this became A, E, S, T here, right? If you divide it twice, so differential twice, you can have A, this is a very good properties of this exponential functions. So you can have A, S2, EST, you bring this here, I bring this here. So we got S squared EST, then K A EST. Then A is the same, you bring the A out, and EST the same, you bring the EST out. So finally we can get this equation. So MS squared here, and this is K A EST equals to 0. This is what we call characteristic equation. characteristic equation. This is the common way. Okay, this is actually the classical way to solve this problem. Because just now the method one is just based on physical observation. So if you solve this problem purely from the mathematical theory, we need to use this way. Even for the damping case, when we're dealing with the damping case, we also use this way. So we call this equation as a characteristic equation. So characteristic equation. So the A cannot be zero. Because if A is zero, which means A0, this one is zero, which means the structure doesn't move. So it's meaningless. There is no meaning for this case. So it's a solution, but it's a meaningless solution. So we cannot allow A to be zero. And this exponential function cannot be zero. You know this, right? From the mathematical theory, the EST is not zero, never be zero. So this one can be cancelled. So we have this equation here. So we have this equation. This is called characteristic equation or eigenvalue equation. Sometimes we call it eigenvalue equation. So from this equation, you have two imaginary roots because s squared equals to minus k over m, and k is real, positive real, m is positive real, and they have a minus k. So you have, if we define the k over m, k divided by m is omega 2, omega n and then squared. We define this. So this is a new sample for the k over m. So we have two imaginary roots for this system, which one is s1 I omega n, s2 is minus I omega n. And the I here is the imaginary unit, which is minus 1 root of minus 1 here. And omega n equals to the k over m, k over m. So then, because we have two roots here, and from the mathematical theory, we know that the general solution or the complementary solution of the equation of motion should be A1 E S12 plus A2 E S22. So if we bring this two here and here, the final the expression for the solution, for the final solution should like this. So it's like this. So many students become confused here because this is imaginary expression. So we have I here. So what is the meaning of this I? And what's the meaning? How can we use this equation? So here is a point. Here is a key point. You should know that the A1, A2 here are complex constants. They are not real constants. At the very beginning, this A, this is a complex variable. Okay, complex variable. And here is a complex constants, which means you have real parts and imaginary parts, which means that the A1 can be expressed as A1 are real parts plus I, which is this I, and plus A1 imaginary parts. So imaginary part. So which means that A1 can be expressed like this. A2 is similar. So A2 can be expressed as A2 real part plus I A2 imaginary part. So these two are complex constants. And this exponential function with the I here, we can also express it into harmonic ones using the Euler equation. The Euler equation here, which is EIx equals to cosine x plus I sine x, plus I sine x. So which means we have two expressions for these two exponential functions. And then go back, you can introduce the Euler equation here, and express the A1 as this part, A2 as a similar part, and which give you like this. So this one is A1 real, A1 imaginary, A2 real, A2 imaginary, and this one became this part, and this one became this part. You can have the final expressions like this. So the A1 real, A2 real, cosine omega t, then A1 imaginary minus A2 imaginary sine omega t and plus I. This is imaginary part, A1 I, then plus I squared. So by using the Euler equation, we can express this solution here. Okay, here. Again, it seems we didn't solve the problem. We still have this part here. We don't know how to deal with this for a real vibration. So here's the point. Here's the key point. And also it's in our textbook by Professor Koff. Because the free vibration is real. It's real physical phenomena, which means you have a structure, you introduce initial displacement, then release this, it starts to vibrate. It starts to vibrate, which means this vibration is real. But this is the function, this is a mathematical function we're going to describe this real function. But this real phenomena, so it's real phenomena. But we have imaginary part here. It seems they are not, they have conflict between this physical phenomena and the mathematical expressions. They have conflict. They are not comply to each other. So the function seems doesn't support the physical real phenomena. So how can we solve this problem? Which means, how can we make this mathematical equation, mathematical expressions to express the real phenomena, real physical phenomena? Anyone can give me an idea? Because we have this part here, which is not complying with the real phenomena. Because the free vibration real exists. It's a real thing. But you have an imaginary part here. So to make these two agree with each other, we need this part to be zero, this part to be zero, which means the imaginary part here to be zero. So this is the key point. If you don't understand it, you cannot understand all the things written by Professor Koff. Okay? Because this is the whole thing here is from the mathematical theory. And they are true. But also the phenomena is true. The same, they don't comply with each other. So how we make them agree with each other? It should be this one becomes zero, this one becomes zero, so this part becomes zero. That's the solution. That's the reason. So if this one becomes zero, which means this one equals to this one, so equals to this one, minus. So this one became 2 because 2A1, because this one minus here. So you have a minus, so it could be 2A1, 2. And this one also the same, so this one became 2. 2, double of this, double of this. So this part cancel. It's like you can rewrite this like different solutions, like different A, B. So the key point here is the free vibration must be real. So the free vibration must be real. So this is in our textbook. So this part, this part, because these two are the same, so they became a new A. Let's see the new A, which is equals to double AIR. And this part, let's say, became a new B, which is equals to double 2A1I. So this part became A cosine omega t minus, or it doesn't matter, minus or plus, because you can introduce the minus or plus here into the B. So it became A cosine omega t plus B sine omega t here, which means we go back to the method 1 by the physical observation. So again here you introduce initial conditions 0, 1, 0, so A equals to this one, then velocity you got b equals to this one. So we get the solutions. So here the a and b are real constant, because they're from here. They're from here. This one is real, this one is real, this one. So this is the final solution from a different way. So this is the free vibration of the non-damping SDF system. And let's summarize the things is like this. The whole solution is here, and velocity, acceleration, introduce this one. So the final solution is like this one. So like this, you can have two ways to derive this. Again, I need to remind you that this equation you must remember, or you must know how we derive this equation, because this is the base for many things we're going to study. So any questions this part? Okay, if you don't have, we'll move on. If you have it, just later you can ask me. So here
Excuse
we
me,
have the
sir.
first. Please.
Can I ask a question?
Yeah, make
sir,
it
can
fast.
sir, previous slide, sir. Can you show the previous slide, sir?
This one?
Not previous one, sir. Previous one. Yes, sir, this one. So you
This
just
one?
said that yes, this slide. You just said that according to Cuff, the imaginary part will become 0.
Mm-hmm.
Sir, do you mean the complete red portion or the constants you are talking about, the A1i or A2i? Because as you see in this solution, there is a complete imaginary part and a real part. But we can also see that the real part also include the imaginary constants. So are you talking about the imaginary part that will be 0, or you are talking about the imaginary constant they will be 0?
I cannot understand your question clearly, but I try to answer your question because this is the equation describe a real vibration, which does exist. And because you have imaginary part here, which means it cannot to describe the real vibration. So to solve this problem, you must have this part became 0. The whole imaginary part became 0, or for any time instant. So this one cannot be 0. This one cannot be 0, and so you need this coefficient of this cosine part is 0, which means A1 equals to minus A2i, which means these two are the same with the minor. So this 2 becomes 1 because A1i, let me see, A1i equals to minus A2i, sorry, minus A2i. A2i. Then this part becomes 0. Okay, this part becomes 0, and A1r should equals to A2r, and this part became 0. Then the whole imaginary part became 0 for any time instant. Then because of these two are the same, so these two are the same, you see here, so it became a double of either this one, they are the same. So we use a new variable a, which equals to 2 times A10, and this one because A1i equals to minus A2i, so the minus A2i again equals to let's use the new sample P, which is 2 times A1i or A2i. So this AB a real constant.
Okay,
Is this
sir,
your
got it.
question?
Yes, sir. Thank you, sir. I
Mhm.
got it.
Okay, because if they have something here, which means you have imaginary part, that means not real, but the vibration is real. So you must have the imaginary part become 0. Therefore, we can have a mathematical expression to describe a real phenomena. real vibration. If you have imaginary part here in this equation, it cannot be used to describe the real vibration because you have imaginary part there. So this is the key things. The free vibration must be real. So the imaginary part must be zero. Must be zero. So this is the whole thing we derive this. So finally we get this equation, final solution for the free vibration. And then we get a very important dynamic properties as just now some student asked the tall building, short building, they have different dynamic properties, which is shown in their K or M or another parameters. So we just now we introduce this omega n, which is natural circular frequency of vibration. So the definition is K over M, then the square root. So square root. Let's see frequency of vibration, natural circular frequency of vibration. And the T is natural period of vibration, natural period. At Fn, we call natural circular frequency of vibration. The three, they can change between each other, but they are the same meaning. They are the same meaning. This is the important dynamic properties of the structure. So this is very important. Let me go back to the question just raised by our students. If there's a tall building and there's a short building, which one have longer period? Am I clear? So if you have a building which is 100 meters tall, you have another building which is 20 meters tall. Let's say they have the same material. Which one have longer natural period? The tall one or the tall one, right? Are you saying the tall or the short one? Yes, the tall one. Okay, the tall one will have the longest period. Let's say you have the tallest one in the world, which is about 1,800 meters. The period of the structure, my guess is about, it should be about 15 seconds, which means you start from here, 15 seconds, which will vibrate here, then back here, here, and to the original. It takes 15 seconds to finish this vibration, the whole circle of vibration. And a shorter building, like if you have a 10 minutes, 10 meters high, about 3 stories, it should be about 0.3 seconds, 0.3. So it's very fast, right? It's very fast. The time is very, very short. So why this thing is very important. What is the dominant design load for tall building? It is wind or earthquake. Anyone knows? Wind. Or there's a two building. One is a tall building. One is a short building. The wind, the effect of the wind is important for which building? The tall one or the short one?
The tall one.
The tall one. Why?
Because.
Why? Because yes. Because what?
Because
That's what period is.
as we know.
Sorry.
Because at the middle is not that much flexible.
We will know the exact reason. The reason I said, I think you're saying is right. Is resonance. Later we'll know this word resonance, because the wind, the period of the wind is about 1 minute or 10 seconds to 1 minute. I mean the turbulence part. And if the tall building, like we just mentioned, the tall building have a lower frequency and longer period, they will cooperate with this wind, which the wind will generate a resonance case, which is a dangerous situation. And for the shorter building, because the natural period is short, which is away from the main period of the wind, so they are not very significant due to the response is not significant due to the wind load. So this is why this is a very important properties. It's like the height, the body weight of a human. If we are trying to understand the dynamic behavior of a structure, first thing we need to know it is natural frequency or natural period. Then we know it's a basic behavior of the structure. So this is very important dynamic properties. Let me show you some examples. This is the tallest building in the campus of Tongji University. This building is 100 meters high, and the natural period of this building is about 2.22 seconds. So 2.22 seconds. And this is a very famous building in Shanghai. Well, later when you came here, you can visit this building. They have Skywalker here. You can walk here. So it's like a sky bridge here. So this building is about 500 meters, and the natural period is about 6.25 hertz, which means if you vibrate, it's vibrate to this end. So vibrate here, then back to the original position. The whole circle, it takes 6.25 hertz seconds. This is a Tumu building. I'm right now. I'm here teaching you this course here behind this window, and this building is a steel building, and the natural period of this building you can see is 0.6 seconds. So 0.6 seconds. This is once the longest suspension building, suspension bridge in this world. This is in China. You have a main length is 1,377 meters. I mean this span, this main span. So this is its period. So this is period. So this is very important when we describe a structure, especially very tall, very long building. We need to know its natural frequency. So this is so we have many ways to determine the natural frequency of a structure. Here is an example. I give you 1 minute to calculate what is the natural frequency of this structure, of this system. So we have a mass. We have a spring which is massless. So we hand a mass to this spring, and the static deformation, not dynamic. Static deformation of the spring is 0.8 centimeters. So what is the natural frequency of the system? So I give you 1 minute to try to calculate this. Anyone?
Yes.
What is the value? Omega? 1,000? What?
225.
Yes, very good. So it should be like we define this. So K over M, because from the definition we introduce G, gravity here. Then we change the divided K, because this is static. This is a static deformation. So we can have natural frequency of the system. So by this simple way we can calculate. We have many ways to determine the natural frequency of the system, because it's a very important properties. And like we just know 1 over delta, because like the static deformation, and here G over delta is T. So we use this equation to calculate this. So the free vibration, if we know there's an initial displacement, initial velocity, what is the time history of the free vibration? It's just like this, the solid line here. So you have initial displacement, which is this value, initial displacement, and the velocity should be this, the tangent part, the tangent angle of this line, and this is the initial velocity. Of course, see negative it will like this, so down. The positive is up. And you can see because there are no damping, so no damping, the amplitude of the vibration will not decrease with the increase of the time. So and a certain, we have a certain, so this is a vibration period. This is a period from this peak to this peak. This is the Tn. And from here, the bottom to this bottom is also Tn. So it repeats itself. It's a periodical vibration. It's a periodical vibration. So let's try another situation, another example. So we have a SDF system shown here. A mass drops through a height h and sticks to the m1. So sticks to the m1 without rebound, which means there's no energy loss due to the impact. Then we need you to determine the subsequent motion of this system, and we give you the reference position. The reference position is taken as the static equilibrium position of m1 plus m2 and k. So f and k. So this is a example. This is a let's do this together. So of course we're going to calculate actually the free vibration of this system, right? Because you have something drop, then cause this structure start to move. So we need two things for free vibration. We need initial displacement and initial velocity, right? Initial velocity. And the time instant is at the impact. Time instant 0 is at the impact time. So here, okay, here. So what is the initial velocity? How we calculate initial velocity? So anyone? So the mass drops here, so they cause velocity at this part, at this time instant, just before impact. So how we calculate this u?
Can we use
This u should be
energy
m1
method?
mu square equals to what?
MTH.
Equals to mgh, right? Okay,
MGH.
that's it. mgh. This is very simple, I think, from high school, right? And this in China, this is from high school. So this energy balance due to the potential energy, so they have velocity here. So after the impact, there's no no rebound, so no energy loose. So what is the initial velocity of the whole system? M1 plus M2. What's the value? It should be M1 because their moment balance should be M1 plus M1 u dot 0, right? You know this, right? Impact, right? Impact. So we have another velocity. So the moment should be balanced. So this is actually this is the initial velocity. What is the initial displacement? So I give you the initial velocity like here because the time instant is 0 at the impact. So the velocity of the m1 plus m2 should be calculated like this. So it gets the initial velocity. So what is the initial displacement? Let's see, the initial displacement is measured from the static equilibrium position of minus of m1 plus m2 and k. And this is a positive. Let's see, this is a positive direction for displacement. So my question here is, what is the initial displacement?
mg over k.
mg over k. Very good. So I forgot to ask you whether the manners, there should be manners there. Because you have you already compressed, right? Compressed, and that's 0. And positive, the positive direction is down. So it should be minus mg over k. Okay, minus. You have a minus here because it's not the positive direction, negative direction. So it's negative mg over k. So this is initial displacement. So once you get the initial displacement and initial velocity, you can directly calculate, you can directly have the answers for the vibration. And the fundamental natural frequency of the system, of course, is here. And then because that's why I said you need to remember this equation. This is initial things. And introduce what you get. This is minus mg over k. And this is initial velocity. So they have this, we have the final motion of the system after the impact, so this is actually this problem seems very simple, but you have many applications. I don't know in your country what is the situation. In China we have the earthquakes, and in some cases, see, this is the structure. This is something dropped due to the earthquake. Some heavy things. Let's see the collapse of the upper floors. Then this is the bottom floor. So this is bottom floor. We have we can simplify the SDF system. We have something dropped here, and if we need to ensure the safety of the structure, the bottom structure. Say if you have some important facilities here, and you need to calculate this, and the whole thing is like you can simplify it in this case, like SDF system with something dropped from the top, and what is the dynamic, or what is the total displacement of this the bottom structure. Then you can calculate whether it's safe or not due to this drop of heavy things. So this is it seems very simple, but you can use it in many problems, many real problems. Okay, so we have finished our second class. I think we have another 5 minutes break. Okay, 5 minutes break. We'll have a break. The mathematical spread. And then start from here. We have another rearrange. We need to rearrange this equation again. We divided both sides of this equation with m, which means m divided here, so m disappear, and k over m equals to omega n squared, so omega n squared. And this part we define, we introduce a new sample, a new variable here, this zeta. We call this damping ratio, okay, damping ratio. So from this equation and this equation, you know the damping ratio should be C divided by 2m omega n. So this is the definition of damping ratio here. After we divided m, both sides. And you can have different expressions for the damping ratio, like if you introduce omega n, which is k over m, then introduce m into this square root samples, you got k times m, and 2c divided by this part. And we define this part as C critical. Okay, C critical. C critical means C critical damping coefficient, which is the smallest value that stops the vibration. Which means if your system have a critical damping coefficient like C critical, it will not vibrate. No matter what the initial condition introduced, it will not vibrate. So this is the smallest value. The smallest value. This is a critical coefficient, and the C is the real one. So that's why it's called damping ratio. It is the ratio between C and C critical. C critical. So this C we call damping coefficient or damping constant or damping parameters. They have different name for this C. And because this is a ratio between these two, so it's called damping ratio. It's a fraction of the critical damping. So you see, we have a new things here. Just now we know the natural frequency. Now we have the damping ratio. Damping ratio. So with this, again, we have the solution, assumption for the solution like here. And then we introduce this into here. So which is AS squared EST for MU two dots, and AS EST for the U dot. And then it brings to here for the K. And after you cancel AEST, it's similar to just we derive the equation of motion for the non-damped system. So you got the characteristic function or the eigenfunction, like S squared plus this things like here. So this is the characteristic function for the system with damping. So again, from this characteristic system, we have two roots, right? Because this is a power of two. This is second order equation. So this is second order equation. So for two roots, so we have two roots for the system. So the two roots from your mathematical theory, you know the two roots should be expressed like minus theta omega n plus minus I omega 1 minus theta squared. Minus theta squared. Again, this is imaginary units, okay, imaginary units. So we have two roots, so two roots here. And the expression of the two roots depends on the relationship between 1 and zeta. So whether this one is larger than zeta 1 or smaller than 1, so smaller than 1. So we can discuss this situation. We have three different cases, different scenarios. So one is if this zeta equals to 1, which means the damping ratio is 1, or C equals to C critical. C critical. This we see, or we call it is a critically damped system. The critically damped system. So when you have this condition, and this part becomes 0, because this one is 0, so the whole thing is 0, and you have two similar roots. So you have two same roots. You have two S1 and S2, so S1 and S2. You have two same roots. So because the two roots are the same, so from the mathematical theory, you cannot directly write like just now we use. Let me go back quickly. Very quickly. Here. Yes, here. So we have two roots. So we write it A1 ES 1 2, A2 ES as 2T. But here S1 and S2 are the same for the damping case. So you cannot use this one. We need to change the form of this solution. So this is from the mathematical theory, and then we need quickly go back here. So we need to change this. So we need A1 here is T, then E minus omega and T. So minus omega and T. So this is the solution, the final solution for the expression for the critically damped system. And then you can introduce initial conditions, right? You can initial velocity, initial displacement. You can determine A1 and A2. You can determine A1 and A2. So if you times 0, so this part became 1. So this is 0. So this one is doesn't matter. So A1 equals to U0. Okay, U0. And similarly, you can get the A2. You can get A2. And by combining A1 and A2 together, you can get the final expression for the critically damped system. So critically damped system. So this is a solution of critically damped SDF system due to initial conditions. So initial conditions. So this is one case. The other case we call lightly damped or small lightly damped SDF system. So we have a small damping ratio is lower than 1, or C lower than C critical. So C critical. So which means this part is positive, because this one is lower than 1. So this part is positive. And we further define, let me show you.
This to simplify the expressions, we usually define this part as omega t. Okay, omega t. We define this omega n times this one as omega t, as omega t. And then the solution will become this part plus and minus I omega t. So these two different solutions. Okay, different solutions. And because you have two different solutions, you can write it like this. So it's actually a, because you need a, let me remind you, a1, a1 e s1 t, and plus a2, a2 e s2 t. Then S1 is like this because the properties of the exponential function. So you can take this part out. So take this part out. Then you bring this to finally you rearrange this equation. It's like this. So A1 sinks and A2 sinks. A2 sinks. And from here, similar to the STR system without damping, we can determine A1 and A2, A1 and A2 because you can further use the Euler equation and A1 here something you can determine. You can determine this. You can determine the the A1 and A2 things. You can introduce initial conditions to determine the A1 and A2 values. So finally, you get this equation. You got this equation. So you can derive this after class from here to here to get the this is the final solutions. This is the expression for lightly damped system. So lightly damped system, because for many civil engineering, okay, for many civil engineering, the damping ratio is very small. Anyone knows the damping ratio for a normal structure? What is the value?
Well, 0.1.
0.1.
Less than
Right.
0.1, less than 0.1.
Less than 0.1, yeah?
Less than
Normally it
10%.
should like 0.05, okay, 0.01. So 1% like that. 0.1 we have that, 10%, but a very special case. To my knowledge, I think a very special case we have the damping ratio for 0.1 or 10%. So which means it's very small, okay, very small. So we're dealing with lightly damped system in civil engineering. So this equation is very important. Again, this equation you need to remember. Okay, you need to remember this. You need directly write down this. If I ask you what is the solution of STF system free vibration case like this, you need to write it down. So we have two equations to remember now. Actually one, because if you remember this one, remember this one, when the damping ratio is 0, this one becomes 1, and omega d becomes omega n, because you see here, because this is 0 now. This became 0, no damping. So the omega n, and this part is 0, because this one is 0, and this is omega n. So it becomes the free vibration of non-damping case. So you need to remember this equation. This equation is very important. This solution is very important. And this is two cases for the two solutions for two cases with and without dam. So because it's under damped system or lightly damped system, this is a solution. And sometimes you may see in a different way, it expressed in a different way. Like you combine this thing and this thing together, and you combine this together, you use the trigonometric rules. You can express it like a e minus theta omega n t e sine omega dt plus phi d. Again, this is the angle. Sometimes it's minus, sometimes cosine. I will not repeat this again. So it's like this is amplitude. This is the vibration amplitude. And for this case, if you have use a sine here, the phi d, it should be phi d. Okay? Tangent phi d, it should be like this. Okay? Phi d. is this. If you express this as a sine omega t, sine phi d, then cosine, then you got tangent with the uptangent, like that. You can get the beta, C phi here, okay, phi. So this is the solution for underdamped system, the underdamped system. So let's summarize this. We have, if we assume that the solution is like this this form, and have two rows, depends on the value of damping ratio. We have different cases, and undamped, critical, and overdamped. We also have overdamped system, which means the damping ratio larger than 1. And this is very rare in civil engineering, but it's very common in mechanical engineering. If you're dealing with automobile, car, train, dynamic system, they may have a very large damping, or sometimes larger than 1. Overdamped system. And normally in civil engineering, we're dealing with this. So lightly damped system or underdamped system. So this is the things. And if we see the time history, because there is damping, so you have an initial displacement, so the start vibrates, and at each circle, it is the amplitude will reduce because there's damping. And this one is critical, right? Critical one, overdamped one, overdamped one. So they have different situations. And we can discuss about the effect of damping. So what's the effect of damping? First, the damping will reduce the natural frequency. The damping will reduce the natural frequency. You can see omega d equals to omega n times 1 minus theta squared. Which means if you measure, if you're going to measure a structure's vibration, let's see, you have this one. You have time history. You measure the free vibration of the system, which reduce, and from this peak to this peak, the time is Tn. Is this time Tn? If you measure the free vibration curve of a lightly damped system, this is a free vibration curve due to an initial displacement. So if you have one peak here, one peak here, the time between these two peaks, it is Tn or Td. It is Td, okay? If you from real structure is Td because damping is there, okay? So this is why we're saying existing damping will reduce the natural frequency or make the period longer, okay? Make the period longer. Now this is Tn, and this is a longer Td. This is longer Td. But for normal structures in civil engineering, omega d is very close to omega n, very close to omega. So we can compare this. So this is damping ratio from 0 to 1, 0 to 1. And this is omega d over omega n, or Tn over Td, the ratio. This is a natural frequency. We call damped natural frequency. This is damped natural. This is natural period. This is damped natural period. Okay, this is a frequency. And you can see when the damping ratio is below 0.2, the two are very close. Okay, very close, which means omega n very close, omega d very close to omega, very close. But they are not. They are not the same. You should know they are not the same. No matter how close these two are close, they are not the same. You cannot use them as the same. So you can approximately use the value, but they are not the same meaning. No sound? Can anyone hear me?
You can hear.
Someone say no
Hey.
sound.
No, we
Okay.
can hear.
Okay, thank
We
you.
can hear you.
Okay. So we can see the effect of the damping will first reduce the frequency and then it will reduce amplitude. We can see if the damping ratio is 2% and starting from 1, this is, if we connect the peak, this is exponential, it should be the exponential part, minus zeta, omega, and t, should be this. So it's exponentially reduce the amplitude, okay? Exponentially reduce amplitude. But if the damping ratio 5%, you can be very significant. With 10%, 20, almost 5 cycles will stop. The vibration almost stops, which means if you lightly damp, it will take longer time to reduce. Very short, very large damping ratios, it takes a very short time to reduce this. For smaller time. So I just give you the solution for overdamped STF system. We will not derive this. So if you are interested in overdamped system, you can use this equation. This is for overdamp, and this one is for critical damp. But in this, in civil engineering, we normally deal with lightly damped system. Any question?
Yeah.
Please.
About the TD. Since this one is like we have decay of motion, how can we define the TD according to the figure? Is it the first period, or I mean, if you have the figure, I mean the vibration, so the TD, is it the first? I mean the first cycle?
Every cycle is TD. For every cycle. Actually, it's not every cycle. Every same things you can see from the bottom to the next bottom. This is TD. You from here, first 0 to next 0 with the same velocity, because the velocity is here, velocity is here. This is TD. And from here to here, because they have the same velocity here, so this is one cycle. For every actually cycle, we are the same TD.
So it means the period does not reduce, but only the amplitude, right?
Yes, the TD will not change. The TD will not change. The TD is the same. You see here, the TD is a constant there. Because the damping is constant. It's like this. Normally, if the structure have no damping, let's say it's Tn is 1 second. Let's say it's 1 second. Okay. If there's a damping there, this TD maybe became 1.05 second, became longer, but it's a constant value. It will not change for each vibration cycle. Am I clear?
Yeah.
Okay, this is very important. It doesn't change. The TD doesn't change for different vibration cycles. Theoretically, it's the same. Okay, it's the same for the theoretical lightly damped system. It doesn't change. Any other? Can anyone give me an example for overdamped system? No, as I said, normally we discuss with lightly damped system, but sometimes we must have overdamped system. We must have it. Otherwise, it will have trouble.
Close the door. Maybe
Sorry?
closing the door.
Close the door.
Yeah.
Someone said. Okay, that's a very interesting example. Close the door. You have some door. They have a spring or dashboard there. So when there's no damping, if you close the door, which means when you push the door away, open the door, which means you push the door away, which means you introduce initial displacement to the system. So after you release this door, it starts to vibrate, free vibration, right? If there's no damping, then this door will start to vibrate, never stops. You can imagine that. I don't know whether you can see my face or see my gestures. You can imagine it. if the door is the SDF system, you open the door, which means you introduce initial displacement. Well, after you release this door, it starts to vibrate. If there's no damping, this door will vibrate forever. But if there's a lightly damping, then the door will vibrate for a while. Maybe it hurts the people who are after you, because the door is like this, right? Like this. So overdamp system. This is a very good example. The door will closely, there are no vibration, so will slowly go back to its original position. So after you push this away, it will go back. Push it away, go back. It will not like this, not this. So this overdamp system. And the seat of your car, if you have experience to running, to ride a car, I think you have this experience. The seat of the car can be simplified as an SDF system. Your body is a mass, and the car itself can be modeled as a stiffness, as a spring. Then also a dashboard, And when the car is running across some roughness surface, a bump, then because there's an impact force or the change of the velocity, so the seat will start vibrate because there are mass, there are stiffness, and there are initial conditions. So if the seat is the lightly damped system, which means after each pump, it will vibrate like this. So it should be an overdamped system, which means after the release from the initial displacement velocity, just quickly go back. It's slowly, directly go back to the original position. It will not start for a while, or start vibration. Okay. So, so the damping is very, very important. Okay, the damping is very important. And today we may have homework for this, how to determine this. The damping ratio, So here we will discuss a way how we determine the damping ratio for a real structure from its free vibration curve or figure. So just now we know that for free vibration of a damped system, this can be expressed like this, this amplitude here, like this. So this is the curve. Let's say this is the free vibration curve we measure for a real structure, So how we get this, which means from here to here. So let me discuss this one by one point by one point. So this is the first peak of the of the free vibration curve. So the first peak, or the peak at time ti, okay, time t. So which means you have ti here. So you have ti here, you have ti here, which give you the amplitude, which is ai here. Ai equals, actually here is ai. Ai equals to a times all these things. So this is the amplitude from this equation. This amplitude at this time is. And another peak. Just ask me the question. Another peak. The duration is td. The td is constant. It doesn't change. So at another time instant ti plus 1 is after td. The amplitude here will become a. Let me write this down. ai plus 1 equals to a. A is the same, doesn't change. This part a. Then e. All these things I will escape, which ti plus 1 here with ti plus 1. Ti plus 1 means ti plus td. Okay, are you following me? Which means this part, this is ti plus 1 here. Ti plus 1 means ti plus td. So ti plus td. And inside ti plus 1 here should be ti plus 1 here, but ti plus 1 means ti plus td, and td is the period. So ti, this part at this time are the same. Are you with me? I think you have a sine part here, which is sine part. This part omega. Let's see, just to simplify as ti. Okay, And this is Ti plus Td, this is Ti plus 1. This is also, we have a sine part here, which is Ti plus Td here. And these two are the same because sine wave is a Td. After a cycle, the value is the same. So you can cancel this. So you can cancel this, which leave you only this part, okay? Only AEI minus this Ti and this Ti plus Td. And again, you can minus this, you can cancel this because they have the same starting amplitude A, you can cancel this. And because the very good features of the equational function, from here you can divide it means minus. So minus here, minus here, it becomes you can express this one. So this thing also cancel, also cancel. So give you only this value, which means the ratio of this peak over this peak equals to this one. Okay, equals to this one. And if we introduce ln operation to the both sides of the equation, so ln here and ln here, okay, ln here, we name this as delta. So ln ai over ai plus 1 equals to zeta omega and td. Okay, so this one equals to this one. So again, we introduce the td. The td should be 2 pi divided by omega d. Omega d. And omega, here, n is missing. Sorry, n is missing. Now, because omega n very close to omega d for civil engineering, so we can cancel this two. Approximately, we have delta equals to 2 pi zeta. That should be zeta. Zeta, epsilon, they are the two variables very commonly used to represent damping. So this is the damping ratio, and which means this one equals to this one, and the damping ratio will be this delta divided by 2 pi. Okay, divided by 2 pi. I hope I'm clear. So if I give you this curve, okay, I give you this curve, which is measured from a real structure, and you can determine this peak and this peak from the curve. Then you divide this one by this one and take a long operation. You got delta, and delta divided by 2 pi, you got damping ratio. You got damping ratio.
pensava ao veduti teatri.
And I think some things. Okay, please close your switch off your microphone. So today, in today's homework, I give you this curve. I give you one curve from a real structure, and I need you to determine the natural frequency and the damping ratio of the structure. Okay. So today we have one homework. I give you a data file which is 2 columns. This column is t, time, and this column is amplitude. If you plot this data in a figure, you will have this curve, similar to this curve, and you need determine. Then you use this curve. You need give me the frequency and the damping ratio of the system. I hope I'm clear.
Professor, can I ask a question?
Sure. Please. Please.
The amplitude is increasing from the initial one.
From what?
How can the initial condition? And it is a single degree of freedom system and no force is applied. How the amplitude is increasing from T0 to Ti.
From Ti. Then what?
T0 to Ti. The amplitude is increasing.
Because there's the initial velocity. You see, this part is below initial displacement, and you have initial velocity, right? We have initial velocity, which give you this one is initial displacement, and this is initial velocity, so it increase. Although there's no external force, the amplitude still increase between this time period from T0 to Ti. Is that your question? Let me show you this figure. Maybe much easier for you to understand. I think I show this some here. You see, you have initial displacement here, initial velocity here. Then, because the initial velocity is positive, it means increase the velocity, increase the displacement, so it increase. So after this point reach the maximum, they start to vibrate at this period, at this amplitude. And if there's damping, then start from here it can start to reduce the amplitude. Is this your question?
Then we are considering there is some velocity, initial velocity in this system.
Initial what?
Initial velocity.
Initial
in this system.
velocity. Of course, you need. This is a very general case. Okay, this curve represents a general case. If you have all. What's that? If you have only, let's say you have only initial displacement, you start like this. Because there are no initial velocity, so it starts from the very beginning and reduce. Which means I'm saying that this is a very general case. We have initial velocity, initial displacement. So at the very beginning, from 0 to this time, to the first peak is like this. If you don't have velocities, then it's just reduced from the start, from the very beginning, because there are no velocity. Okay? Clear?
Okay, thank you. Clear.
Mm-hmm. So let me finish this example. Then, if you have any questions, we can discuss this further. Just now we use these assumptions that the omega d equals to omega n. Then we can cancel this, and then of course you can use this equation. This is exactly solution for the damping ratio. You can solve this equation to get the real exact solution, not approximately solution 2 pi times theta. But they have a very small difference when the damping ratio is very small. You can see this is a real exact solution for the delta, and this is approximate solution, and they are very close. They're very close. So let's see this example. So we have a frame which can be modeled as SDF system. We put 2 centimeters away from its static equilibrium position by a rope. Let's see, we push this structure away using the rope. We pull this structure away from its original position. And the force measured was 16.4 kilonewton. Like here, the horizontal force is 6.4 kilonewton. And the rope was suddenly cut, which means you pull this structure away, then suddenly cut the rope, then the structure start to vibrate. And the frame vibrates freely for 4 cycles in 2 seconds. 4 cycles in 2 seconds. And the vibration amplitude reduced to 1 centimeter. So this is like we do experiments or do a test to a real structure. This is all the values we did when we did the test. And based on all these informations, I need you to determine the damping ratio, the natural stiffness of the structure, the natural frequency of the vibration, the weight of the frame or the mass of the frame, and the damping coefficients. Almost everything of the structure, or every important dynamic properties of the structure. So you need to use this
measurements. So because of the time, I will not allow you to do this. Let's do this together. First, damping ratio. Okay, damping ratio. So damping ratio, how we define that? We can use the just now we discussed the method we call logarithmic decrement method. So logarithmic decrement method, which is like this is delta. Okay, this is delta, then divide by 2 pi. But here has a j, which is 4 cycles. Let me go back, explain you. I need clean this first. You see, just now when we derive, this is what we call logarithmic decrement method to determine the damping ratio, because this is a logarithmic rule, and this is the free vibration curve. Just now we use the peak here and another peak 1 TD away. So if you use another peak, you use a peak here, which is I2, I plus 2, which give you here a 2, here a 2, here a 2, and here a 2. And after you divided this, you have a 2 here, right? You have a 2 here. So you should divide it, delta divided by 2 pi and another 2. And similarly, you have a 3. You have a 3 here, the third peak, which is, this is the first one, the second one, the third one. This is 1 circle, 1 cycle, 2 cycles, 3 cycles, and 4 cycles. And you have a J or N, which means after J cycles. So they are the same. Just now, you need one more variables to describe how many cycles here. So just now the program told you 4 cycles. So we need 4 here, the AY times AI plus 4. Actually, here is 4. So the original displacement 2 centimeters. So after 4 cycles, it became 1. So logarithmic 2 over 1, then divide by 2 pi and 4. So the damping ratio is estimated as 0.0276. Okay, this is one answer. So how about the stiffness? How we determine the stiffness of the frame, the structure? What is the stiffness?
Deflection.
We have the force and the static equilibrium. We can use
Yes. So it's very simple, I think, for you. This is the force we use to push to pull the structure away, and this is static deformation. So this case should be this force divided by this static deformation. So this is the stiffness, the lateral stiffness of the structure. So what is the natural frequency?
We have the number of cycle and the time. So we
Omega
can
T.
use
Yes, one is cycle divided, actually the time divided by cycle, so we know how many times you used for each cycle. So it should be 2 over 4, because 4 cycles, 2 seconds. But remember, this one should be TD. Okay, this one should be TD, not TN. And we need TN. I'll let you know why we need TN soon. And we know TN. We need determine TN for the for the case. Then TN equals to TD times this one, times this one. And we already know the damping ratio. We know that the damped natural frequency TD. So we know that actually the natural frequency of the system, TN. Then we need to calculate the mass. How we get the mass? Can anyone tell me? Sorry? Again?
Root under K by M. Omega n equal
Omega,
to
yes,
K by M.
omega, yeah, very good. Omega, so we need omega. But remember, this is omega n. So if I give you example, a problem like this, you cannot use TD here, although the answer is very, very close, but it's not true. Because this is omega n. It should be omega n, and the mass should be divided by K and omega n. It's not omega d. You cannot use omega d here, although the answer is very, very close. You can try this. They are very close, but they are not the same. They're not the same. They're not the same. So this is the same we discussed, and then you can get the mass. So from this simple test, you can get almost everything of this. So after you have the natural frequency, the damping ratio, the mass, you can get damping coefficient. You can have the damping coefficient. So this is very useful. But I should tell you that this method we call logarithmic decrement method is very sensitive to measurement error or noise. I will not repeat this because of the time, but I just let you know that this method is very sensitive to measurement error. Although your measurement error is very small, but the damping ratio you get maybe have a very large estimate error. You can try this in your homework today. And this is another damping mode. I think today I will skip this. Later on, have time, I will explain this. Okay, I will just explain my today's homework again. We have, I gave you this curve. This curve is from a real structure, okay? Real structure, we measure from a real structure. So when you plot this, it's like this. And I need you to identify the damping of the frequency of the structure using this measured data. I give you the data in a ASCII form. You can open it in Excel, MATLAB, or other. It's a standard data form. So you can open that. The first column is time in seconds. The other column is acceleration in meter per second squared. Per second squared. So you need to use that to determine the natural frequency and the damping ratio of the structures. Okay, so that's all for today's lecture. I see we met next week. Okay, see you next week. I will upload everything that today's homework and PPT